to. If you remember in chapter 1, we talked about transformations. We talked about 3 transformations. What were our 3 transformations we learned? Reflection, translation, rotation. Okay, we talked about 3 transformations in chapter 1. We are going to build on that, and we are going to talk about a 4th transformation today. So the first one we're going to talk about that we did not talk about in chapter 4 is a dilation. Most commonly misspelled word in chapter 4 is dilation. It is dilation. There is only one A. You are not dialing someone on the phone. It is not D-I-A-L, okay? It is D-I-L, dilation. So we're going to talk about a dilation and then what does it mean to be an isometry or rigid transformation. So the first thing you'll see in your notes, if you'll flip back to the front page, is the word dilation. I'm going to add some things that you are going to need to know that are not in your notes. So make sure that you are with me here and that you add these things to your notes. So first of all, what is a dilation? So what do you guys know about dilations? What do they do to your shape? Okay. Make it bigger or make it smaller. We will not use the words bigger or smaller. We will use the words enlargement and reduction. Okay, so you are going to tell me, when you tell me that it is a dilation, you're also going to tell me what kind of dilation is it. Is it an enlargement or is it a reduction? So be very specific. Dilations have a scale factor that determines do they get bigger or do they get smaller. We call that scale factor the letter K. If it's a dilation, your K value should be greater than 0. And if it is an enlargement, your K value should be greater than 1. If it's less than 1, it's not going to make it bigger. If it is greater than 1, it will make it bigger. If it is exactly 1, it doesn't change it at all. It stays the exact same shape. If it's a reduction, your K value should be some fraction between 0 and 1. So K should be greater than 0 but less than 1. So it may be half the size or 3/4 of the size, so it's going to be smaller, or it may be twice the size or 5 times the size, and then it's going to be bigger. So enlargement versus reduction. Every dilation we are going to do is going to have its center at the origin. If you were to change the center, you can no longer write a rule. So if you remember back in chapter 1, we talked about writing a rule for translations, and we only did it for translations. We didn't do it for reflections or rotations. But we are going to write rules today for all of them. In order to write a rule, your center has to be at the origin. So we're going to keep our center always at the origin. If you're looking at a problem and you're like, well, I could dilate it from this point, but that point's not the origin, then I'm not going to let you work it that way. I'm going to tell you you've got to dilate it from the origin and then figure out what to do. So keep your dilation at the origin. The rule is xy will map onto kx, ky, or the better way to write that is xy arrow kx, comma, ky. So what that means is that if it is a dilation, all you have to do is multiply your x and your y by whatever your scale factor is. So if it's 2 times bigger, you're just going to multiply it by 2. If it's half the size, you're going to multiply it by a half, as long as it's centered at the origin. If the center is not at the origin, you cannot just multiply the coordinates by k. Okay? So for example, if you look at this picture here, we have a point xy. If we're dilating it from the origin, we can just simply multiply our x and y by whatever our scale factor is, k. And if it's dilating from the origin, you could draw a line through the origin and it will go right through your pre-image and your image. Okay? So just a reminder that we used those words last time, pre-image versus image. So remember, your pre-image is your original figure, and image is what you get as a result of the transformation. Okay, so what you're going to see next on your paper are the 4 problems that you were supposed to graph. So I've already graphed mine on the board, but you only have one triangle right now, right? Your triangle is the one that is in blue, correct? Everybody's look like that? Okay, so when you get to these problems, we have only talked about one transformation as a rule. Right now, you should be able to look at this rule based on your knowledge from chapter 1, and you should be able to tell me what transformation this is asking you to do. The directions, though, say apply the transformation. When you get to the homework and you see that word apply, the first thing you're going to think is, Miss Lashley said I have to graph it. If it says apply, you're going to grab a sheet of graph paper and you are going to graph the pre-image and the image. Okay, make sure you're clear because I don't want you to miss points. I will be grading your graphs. And then it says, the next part, identify and describe the transformation. From what we've learned in chapter 1, you should be able to look at that rule and automatically be able to tell me what transformation is that and what does it do to the shape. So does anybody remember from chapter 1 what transformation this is? Translation. And what does the -4 and the +1 tell us to do? Okay, be specific. Very good. So when you say -4 on the x, that would be left 4 and then up 1. So we should already know that. This, when it says identify and describe, this is going to be a translation. Left 4, up 1. So remember back to chapter 1 when we talked about identifying and describing, you had to tell me what kind of transformation is it, and if it was a translation, you had to tell me the distance and the direction. So left 4, up 1. Naya? Yes, you can write it exactly like I did on the board. Okay. Now, let's say that you got to the test, though, and you're having one of those days where all of a sudden everything that was in your brain just vanished and you forgot what it was. Ever have that moment where you're like, oh my goodness, I know this, but it's just not here today? If that were to happen, you could take these coordinates and plug them in to calculate the new coordinates. And I want to practice that because that's what we're going to do for the next couple ones since we haven't learned those rules. So let's say that I wanted to find P prime. Remember that when you graph the image, you're using prime notation. So if I want to find P prime, that just means I'm going to plug 1 in for x, 3 in for y. So that means over here I'm going to plug 1 in for x, 3 in for y to get my new coordinates. What is 1 minus 4? -3. What is 3 plus 1? 4. Okay, let's do the same thing for Q. So to find Q prime, I'm going to plug 1 in for x and 1 in for y. What's 1 minus 4 again? -3. And 1 plus 1? 2. And then I'm going to find R prime. 4 is going to go in for x now, and 1 is going to go in for y. What is 4 minus 4? 0, and then 1 plus 1, 2. So now on your graph paper, go ahead and graph P prime, Q prime, R prime on that same graph that you were on where you have your pre-image. Every year I have someone who does not connect their dots, so I just want to remind you that these are supposed to be shapes. You are not just graphing a set of points. Make sure that you're connecting your dots and making triangles or rectangles or whatever the shapes are. Okay, so once you have that graphed, if you weren't sure and you're on the test and you're like, I cannot remember what that rule does, then you could look at the shapes and ask yourself, how do we get the blue to land on the red? Do we translate? Do we rotate? Do we reflect? Or do we dilate? Can you see now that to get from blue to red that you would translate? Okay, and then you could just count. I'm going to go 1, 2, 3, 4. So left 4, and then up 2. Or excuse me, up 1. Look like 2 there, but this is just really wide. So up 1. And that's exactly what we have. Left 4, up 1. Everybody with me? So worst case scenario, you're plugging the coordinates into the rule to find the new coordinates. But by the end of this class period, I'm believing that you are going to know all 4 transformations and their rules, and you're going to need to be able to identify the transformation by just looking at the rule. When you get to the homework, though, When it says apply, you are going to graph. So part B, with me on part B, you guys went ahead and graphed it, but you only have the blue triangle. Is that correct? Or do you have the red one? Yeah, blue one. Blue triangle, right? Does yours look the same? Okay, so we're looking at this rule. We have never talked about this rule. So at this point, we don't know what kind of transformation this is. You don't have the blue or the red triangle on your paper. All you have is the blue triangle. So let's go ahead and do the exact same thing we just did. Let's find our A prime, our B prime, and our C prime so that you can graph it. So if I do that, plug the points in, what is A prime going to become? Very good. 1, -2. What is B prime going to become? 4, -2. And what is C prime going to become? Very good. 3, -1. So now on your graph paper, go ahead and graph those 3 points and connect the dots. And remember on the homework, I'm going to be grading your graphs. That means you have to have the pre-image graphed, you have to have the image graphed. Even if you can look at it and decide what the shape is, what the transformation is, you still have to graph it. If you see those words apply, then you're going to graph. Make sure you label prime notation correctly. Connect your dots. Once you have it graphed, look at the picture and tell me, what transformation is this? Very good. So it is a reflection across the x-axis. Remember back to chapter 1, if you tell me that it is a reflection, you do have to tell me the line of reflection. Did you go across the x-axis, the y-axis, or was it some other vertical or horizontal line or diagonal line? Okay, so let's think about that rule with me real quick. What changed in the rule? The y became negative. So we went across the x-axis, and it was the y values that went from positive to negative, right? Okay, so if we're going across the x-axis, it's the other letter, the other variable that changes sign. So if we were to go across the y-axis, add this to your notes. What do you think the rule would look like if we were doing a reflection across the y-axis? Exactly. So if I'm going across the y-axis, my rule would become xy arrow. Instead of x negative y, it's going to be negative x positive y. Because now the x's are going to change from positive to negative. Does that make sense? So when you get to the test in a few weeks when we're taking our chapter 4 test and you look at the rule, I'm hoping that you'll be able to look at the rule and just say, oh, the y changed sign, so this is a reflection across the x-axis. The x changed sign, so this is a reflection across the y-axis. Everybody with me? Any questions at all about reflections? Okay, we'll go to the next one. Same thing here, you only have the blue shape, you do not have the red shape. This is the rule. We have never talked about this rule in here or what that's going to look like. So you get to the homework. First thing you might have to do is investigate what does this shape look like, doing the same thing we've been talking about. So let's find R prime, E prime, C prime, and T prime. We're going to plug those coordinates into the rule. Be careful on this one. This is the one that a lot of students mess up when they plug their points in. You're going to plug the -3 in for the x. You're going to plug the 0 in for the y. So what is that going to give you for R prime? Okay, 0 is going in for the y, so it's going to be 0 here. And -3 goes in for x, but since it's a minus a negative, that's going to make it a +3, right? So basically what you're doing there is you're switching the coordinates and then changing the sign of the second one. Okay, so if we do the same thing here, -3 is going to go in where the x is, +3 is going to go in where the y is. What does that give us? 3, 3. If you're not following me, be sure to let me know so I can explain that better. See, We're going to plug the -1 in where the x is and the +3 in where the y is. So what does that give us? +3, +1. And then the last one, what do we get for t prime? 0, +1. Questions on how we got those coordinates? Okay, go ahead and graph them on your graph paper. Create your shape. And I will warn you, I mean, the biggest mistakes that I'll see in this section is graphing your coordinates incorrectly. So if you're going to double check anything you do today, make sure it's double checking. Did you really plot the point? Did you notice it was a negative and not a positive, or a positive and not a negative? Be really careful. Bless you. Okay, so now we want to figure out how do we get from the blue shape to the red shape. What transformation does this look like? Okay, I'm here in rotation. It is a rotation. We need to be very specific when we say that it's a rotation. So what direction do we need to go for going from blue onto red? Okay, we won't say right or left. We'll say clockwise or counterclockwise. And so again, if you forget, look at the clock. As the red hand turns, it's going to the right, right? And so that's clockwise. So with this is going to go clockwise. And then you have to figure out how many degrees is it turning. So here is one way that I have found that is the easiest way to figure out your angle of rotation. If you will connect your pre-image point, so just pick a pre-image point. I'm going to pick point T. Our rotations, we're going to keep centered at the origin. So connect it back to the origin. And then connect it to the image point, T prime. That is your angle of rotation. How many degrees is that? 90 degrees. So if you're not sure, pick a pre-image point, pick its corresponding image point, connect them both to the origin, and then look at that angle. Does it look like a 90-degree angle, 180-degree angle, 270 degrees? And our transformations we're going to keep pretty easy in this section as far as they're going to be increments of 90, 180, 270, or then all the way back to where we started, 360. Okay, so if you're unsure, that's one way you can check. You could use any pre-image point. So let's say I went from C to the origin and then to C prime. And again, that looks like a 90-degree angle. So if you're unsure, that's one way you can check. Any questions on that? Okay, so we're going to say rotation clockwise 90 degrees, and then make sure and include your center, about 0, 0, the origin. Because it would be different if we shifted our center somewhere else. Okay? You can only write a rule if your origin is the center. If your origin is not the center, then you cannot write a rule using our lesson today. So make sure that you're keeping your center at the origin if you're trying to write a rule. Any questions here? Okay, last one we're going to look at, and then we're going to come back to this rotation. I want to do one more real quick before we look at rotations further. I'm going to come back to that in just a second. Okay, so let's look at this last one you've already graphed. Again, you only have the blue triangle on your paper, this little blue triangle. We have talked about this today already. Notice what's happening to X and Y in the rule. What's happening to it? Okay, it's being multiplied by 3, and so we just talked about if you take the X and the Y and you multiply it by a number, then that's going to be a what? Enlargement. I do want you to tell me what type of transformation it is before you say enlargement. So what type of transformation is that? Dilation. So I'm going to ask you to give me both words. It is a dilation, and it is more specifically an enlargement. But include both words, okay? Dilation, only one A in the word, and then it is an enlargement. And then what is the scale factor? What are we enlarging it by? 3. That's always going to be that number that they're both being multiplied by. And they will both be multiplied by the same number. So you won't have x getting bigger by something and y getting bigger by something else. We will keep the shape growing at the same rate in all directions. So it's a dilation enlargement by 3. We can tell that already just by looking at the rule from the beginning of the notes. Again, if we didn't know, then we could find our k prime, our l prime, and our n prime by plugging them in and multiplying each one of them by 3. Let's go ahead and list our k prime, l prime, and n prime. And again, all we have to do, since our center is at the origin, is multiply them by 3. So what is that going to make k prime become? Very good. -6, -3. L prime, 3, -3. And n prime, 3, -6. So go ahead and graph that one on your paper and label it correctly. And then there's a couple of things I want to show you once you have it graphed up here, and you need to add these to your notes as well. Sometimes they're not going to give you the center at the origin, which means you will not be able to just compare the coordinates. If the center is at the origin, you could just say, okay, -2 times what is -6? -1 times what is -3? And you would easily be able to tell, oh, it's just 3 times bigger. Would you guys agree? But sometimes the center is not going to be at the origin, so you cannot compare the coordinates if the center is not at the origin because you can't write a rule. So if you are unsure what is my scale factor because it looks like the dilation is not centered at the origin, here's how you can find your scale factor. So K can be found by taking the image distance and dividing it by the pre-image distance. And what I mean by image distance and pre-image distance is pick one side of your shape and find the length of that one side. Compare it to another side of your other shape. So image first though, the image, the resulting figure has to go on top. So for example, let's say that I calculated the distance from L to N here. How far is it from L to N? 3. Always choose a horizontal or a vertical distance if you have one because they're easy and you can just count them. So this is 3 units. So our image distance then for K would be 3 over, and then go and compare it to its corresponding pre-image distance. So what's the pre-image distance here from L to N? 1. And so notice we get 3 over 1, which is just 3. If it's not centered at the origin, that is what you will have to do to find your scale factor. You'll have to compare side length to side length, always putting the image on top, pre-image on bottom. Okay, so how, Anna? Okay, so if it wasn't centered at the origin, then it may be over here, and maybe you have this shape, and you are growing it from this point and making it 3 times as big, so that now your shape is something like, if this kept going, so now your shape is something like this down here, but it's not centered from the origin to make it bigger, it's centered from this point to make it bigger. Does that make sense? Okay, so how you would physically do that would have to be with a ruler and measuring the distance from here to here and then going however many times that distance you wanted to go. We won't be creating dilations not centered at the origin, but you may be given pictures of dilations not centered at the origin. Okay? Here's how you can tell if it's centered at the origin. So let's say I don't know if it's centered at the origin. I look at the picture, I'm like, could be, I'm not sure. Connect your image to your pre-image point and use a ruler and draw a straight line. Do it for every one. Pre-image to image. if I can do this without a ruler. And then pre-image to image. And if I had used a ruler, it would be more precise. But do you see that they all intersect at the origin? Everybody with me? If it's centered at the origin, when you connect the image to the pre-image, your points, and draw a line, where they intersect is where your center is. So if it doesn't all cross at the origin, then you'll know that your center is somewhere other than the origin. Okay? For real good? Okay. Those are the things that we need to know. Let's go back to the rotation. I'm going to ask you to make some notes on your paper about rotation. So find some space. It may be on the back that you have room, where it's blank, whatever, but you're going to need a pretty large square area. So maybe the very bottom back corner. I think there's a big spot down there. We're going to look at all the different types of rotations. So right now, the only thing we've talked about is clockwise. And with clockwise, we said that if we go 90 degrees, the rule is going to be X, Y, arrow. And this is the one that we did that was clockwise 90 degrees, and it was Y negative X. I find that most students have if they have trouble, they have it with rotations. So I always look for little tricks, techniques, whatever you want to call them, that will help me remember what's the rule always going to be. And here's what I found that helps me. So first of all, if you're doing a rotation, you are always going to switch the X and the Y. Every time you do a 90-degree rotation, you're going to switch the X and the Y. So notice that instead of going X, Y, it goes Y, X, right? So the first thing you're always going to do is switch X and Y. The second thing you're going to do is one of those coordinates is going to change sign. Notice that it was the second coordinate here that went from, the second coordinate changed to a negative. Do you guys see that? So the second thing you're going to do is change the sign, but you've got to figure out what changes sign. Is it the first one or the second one that changes sign? So here's how I remember it. If I'm going clockwise, I'm going to the right, correct? So that means that I'm going to change the coordinate that's on the right. So I'm going to switch them, Y, X, and then I'm going to change the sign on the right. If I'm going clockwise, I'm going to the right. So I change the sign on the right. Let's see if that really makes sense when we look at the next one. So if we want to do another 90-degree rotation, so that would make it a total of how many degrees? 180. So if I'm going 180 degrees, I'm going to take my original XY, and I'm going to switch it once, change the sign on the right, which is what I have up here, Y negative X. Then I'm going to do it again with these coordinates. So now I'm going to switch these coordinates, and when I switch them, I'm going to get negative X, positive Y. So all I'm doing is switching. You with me there? And then I'm going to change the sign on the one on the right. That means it's going to become negative X, negative Y. Switch, change the sign, switch, change the sign for every 90 degrees. If you're going to the right, it's changing the sign on the right. Let's do another 90, which would be 270. Means we're going to go from our original XY, and we're going to do a 90-degree rotation 3 times. So the first time we would have had Y negative X. Switch and change the sign. We now get negative X, negative Y. So now we're going to switch again, which is going to give me negative Y, negative X. And then we're going to change the sign on the right. Negative Y, positive X. And we'll come back to that in a second. Yes, good. Are you guys with me here? So if we do it one more time, where should we land? Okay, at the original spot, 360, back where we started. So if I do this one more time, X, Y, arrow, I should end right back on top of X, Y. Would you agree? So let's see if we do. Switch it. So if we switch, we're going to get X, negative Y, and then change the sign on the right. And we get XY. So every time you do a 90-degree rotation, you're going to switch, change the sign. If it's clockwise, it's to the right, so you're changing the sign on the right. Does that help? Okay, let's do counterclockwise. So keep the same idea for counterclockwise. Counterclockwise. But counterclockwise doesn't go to the right. What does counterclockwise do? Goes to the left. So now we're taking a point and rotating it left. And if we're rotating it left, that means we're going to change the sign on the left. We're still going to switch to X and Y. So you still switch the X and the Y, but now you're going to change the sign on the left. So if we're going counterclockwise, we'll change the sign on the left. So let's write those same rules, but let's go counterclockwise to the left. So we're going to start with a 90-degree rotation. X, comma, Y arrow. We switch them, we get YX, but now we change the sign on the left, so it becomes negative YX. And then we're going to do it again for a 180. So 180-degree rotation. Start with our original XY. We've already rotated it once 90, so we're going to take that coordinate and rotate it again 90. So we're going to switch, which gives us X negative Y, and then we're going to change the sign on the left. So now we have negative X negative Y. What do you notice about the 180-degree rotation no matter which one we're doing, clockwise or counterclockwise? They're the same. So when you're going 180 degrees, it doesn't matter which direction you go. That means if you were giving me an answer of a rotation 180 degrees about the origin, you don't have to put direction, clockwise or counterclockwise. It doesn't matter. Does that make sense? So these are the same. Here. Okay, those are the same. All right, let's go to 270. So we have XY arrow. Again, you're going to switch first, negative Y, negative X, and then change the sign on the left. So that becomes positive Y, negative X. And then we'll do it one last time to get back where we started. 360, XY. If we switch, we get negative X, positive Y. And then we change the sign on the left, and we're back to where we started, XY. So if you're rotating counterclockwise, you're rotating to the left, which means you're changing the sign on the left, but switch every time first. What do you notice, and this is what Bree just said a minute ago, what do you notice about a 90-degree clockwise and a 270 counterclockwise? They're the same. If you go 90 degrees clockwise, that's the same as going 270 the other direction. So you could both have, you and your friend could have different answers on your paper and you could both be correct. One of you is going 90 clockwise, the other one's going 270 counterclockwise. That would also be the same here for 270 clockwise and 90 counterclockwise, right? Notice those are the same. All right, any questions about rotations? Not in this class. Yes, there are rotations that are 45 degrees, and if that were the case, again, I would tell you, I would connect my pre-image to my origin and then back to my image. You could take a protractor and you could technically measure that angle to see what was the angle of rotation. Okay, so if you're ever unsure, that's one way you could check it. So maybe you get to the ACT Aspire and they actually have an angle that's not 90 degrees or 180 or 270. But that is how you could check it. You can measure that angle if you needed to. All right. Any other questions? Okay, so the first part of your homework is just simply going to be graphing and then identifying and describing your transformations, which you should be able to do really easily. But again, if it says apply, what are you going to do? Graph, and you're going to graph the pre-image and the image and label everything beautifully so that you can get full credit. Here is the little chart in your notes that puts basically everything we talked about into one location. The only thing it doesn't do is it doesn't give you this nice detailed for every angle of rotation. Okay, so that's why I wanted to add that into your notes. All right, so last couple words here, isometry versus rigid transformation. An isometry is a transformation that preserves the length, the angle measure, and the area. In other words, when you do an isometry, it doesn't change the size, it doesn't change the shape, it stays exactly the same. The lengths are the same, the area is the same, everything about it's the same. Which transformation that we've talked about today does not keep the shape the same size, same area? Dilation. So an isometry would be a reflection, a rotation, or a translation, but it is not a dilation. Okay? So isometries are all the other three. A rigid transformation is just another name for an isometry. So on your vocab test, it'll say another name for isometry. Don't put isometry. That's not another name for isometry, okay? Make sure and put rigid transformation. And so again, rigid meaning that it doesn't stretch it. It doesn't make it. It's very rigid. It moves without changing any dimensions or size about it. All right, and this is where they tell you translations, reflections, and rotations are isometries. They are congruent. They keep the shape the same size. And then it also tells you here that dilations with a scale factor produce images that are not congruent because they're going to make them bigger or smaller. Again, this is important. If K is equal to 1, it doesn't change your shape at all, so it's not a dilation. Dilations have to enlarge or reduce. If it is exactly 1, nothing's changed. Okay, so we're going to use this for the next few examples in the notes. The next few examples are going to say, determine if these are congruent or prove these are congruent. Determine means you could have an answer of no. Prove means it is definitely congruent. Now you've got to come up with how you know they're congruent. So chapter 4 is going to be our biggest proof chapter of all. And in chapter 4, we are going to start writing 2-column proofs again, and we'll spend several days doing that, but it's not today, okay? Today is going to be the other way that we're going to prove shapes are congruent. And the way we're going to prove they're congruent today is with transformations. So we're going to decide, do these two shapes, after these transformations, do they look to be the same size, same shape, same area? If they do, then we're going to have to list the transformations that would prove that. It has to be a reflection, a translation, or a rotation, or it has to be a combination of those. If it's a dilation, then they're not congruent because it got bigger or it got smaller. Is that clear? Okay. So we're going to look at some examples again. Now we're back to you don't have these graphed, so I'm going to give you a couple of minutes. I want you to graph. I think there's 5 examples left in the notes. Is that correct? Look and see. 3 on the next page, 2 on the back. Okay, I want you to take a few minutes and on 5 different graphs, I want you to graph those. This is going to be different though. They're giving you 2 shapes. So you're graphing both of them. Are you with me? So you'll have 2 triangles or 2 rectangles on every graph. Okay, give you a couple minutes to do that. I want you to graph all. Start looking at these next ones. Okay? So again, when you get to the homework and you're given these questions and it says determine whether the polygons with the given vertices are congruent, I'm going to assume you should need to graph these, that you can't just look at these coordinates and decide what the transformations are. So I expect you to graph the picture to show your work, okay? So make sure that you graph, make yourself a note. I will be looking for a graph when I'm grading, okay? So you're going to graph the 2 shapes. They do not tell you which one is the image and which one is the pre-image. And they don't use prime notation, they use different letters. To make it easier for you and for when you're comparing with your friends or when you're checking your answers in the back of the book, the best thing we can do is try to all do the same thing. It wouldn't be wrong if you do it the other direction, but it's going to help me when I'm grading your homework and it's going to help you when you're trying to check your answers if we all assume the first one here is the pre-image and then the second one is the image. Now, you can do it the other direction, but if you do, then your answer may not match the back of the book, or when I'm grading, I'll have to look and see what direction did you go, okay? So if you want to try to be consistent, just when you graph the first one, consider that your pre-image, and then you're looking at the second one as the image. So in that case, we're looking at blue and asking ourselves, when they transformed it to red, did it stay the same size and the same shape? So would you say, yes, these are congruent, or no, they are not? Yes, okay. So when it says determine if they're congruent, you cannot just put yes on your paper. I want you to also include the transformations then that would make the blue one land on the red one. I want you to write it both ways to practice for the test. I want you to write a rule, and I want you to identify and describe it so that we understand how to do both things for the test. So what transformation do you think this is from blue to red? Translation, give me directions. Down 3, left 1. Everybody agree? Okay, so then what we're going to put is yes, translation, down 3, left 1, and then we're going to write a rule that describes the translation, down 3, left 1. Every rule should start with X, Y arrow. And now you tell me what directions and how do I write that? Careful. Down is the Y direction. X minus 1, comma, Y minus 3. It may help you not make that mistake if you describe your translation as left 1, down 3. That way you're doing the X first and then the Y second. I don't care, but I want to make sure that when you write the rule, you've written it correctly, okay? So I want you to do both of those things to practice for the test on every problem. Are we clear what's expected? So graph it, write the rule, write the translation or the transformation. All right, and that's correct. That would work. So let's look at the next one. So you should have a blue and a red again, and we're going to assume the first one in blue is the pre-image, the second one in red is the image. Mrs. Ashley. Yes, ma'am. Yeah, hold on one second. Emmeline, telephone. Okay, so do you guys think yes, they're congruent? No, they're not congruent. Not congruent, okay? So we would say no. But now I want you to tell me what transformations did they use to get from blue to red? Okay, so first thing I would say is I'm pretty confident it's a dilation because it got what? Bigger. So let's start with the dilation. And what kind of dilation does it look like? Enlargement. Okay, so now we need to decide, is it centered at the origin? So remember how I showed you that you can check your center. Connect your pre-image and your image points and draw a line. And do that for every pre-image and image point. Are they crossing at the origin? Okay, and you need to use a ruler when you're really doing this and not do what I'm modeling up here, which is not very good. But it does look like they cross at the origin. Then compare your coordinates then. Remember that it is image over pre-image. If it's at the origin, you can compare your coordinates. If it's not at the origin, you cannot compare your coordinates. So image coordinate here, let's just start with this one, is 6. What is the pre-image coordinate that it corresponds to? 4. And what is 6 over 4 reduced to? 3 over 2, or 1.5. Check that for all of them and see if it's the same. If I go to the y value, -3 over -2, are we still getting 3/2? Okay? Or you could compare distance. Remember, if it's not at the origin, you have to compare the side lengths. So what is the distance here in red vertically? 3. What's the distance in blue vertically? 2. And do we get 3 over 2 again? Yes. Okay? You can only, I'm going to say this again, you can only compare the coordinates if it's centered at the origin. If it's not at the origin, you have to compare the distances. Okay? But either way, this is a dilation, enlargement by a factor of 3/2 or 1.5. Okay, and so then from there, we need to list the rule. So what would the rule look like? XY arrow. Remember, you're just multiplying the scale factor by the x and multiplying the scale factor by the y. So you could put 1.5x, 1.5y, or just 3/2 x, 3/2 y. Write the rule, write the description, identify and describe, even if the answer is no, because now it's a dilation. So no, they're not congruent because you had a dilation. Okay? Any questions on those? You can have a dilation followed by a rotation, yes. I don't know that you'll have any that are that complicated, but you will have some that are multiple transformations. It's just most of them are probably going to be a reflection and a rotation, or a translation and a rotation. I don't think that there's anything on the homework that's a dilation and a rotation. Okay? But you will have ones on the homework that are multiple transformations. It would be more of a rotation and a translation or a reflection, and we're getting ready to do some like that. Okay? But not any that included a dilation as well. Okay. All right, so I'm going to skip this one since it's just another one with the same directions if we're doing okay. Is everybody following, looking at them and comparing and then just writing the rule? Okay, so let's skip this one and then go to this one. So make sure you're on the correct one on your graph paper. And if you haven't finished graphing, this was the fourth one. So if you haven't finished graphing, go ahead and finish graphing that one. The directions change here, though. The directions change to prove that they are congruent. Again, I would expect that you're going to have to graph these before you can even begin to prove that they're congruent. So make sure that you graph them. And then you're going to look at your shapes. This is not a question of are they congruent. They're telling you they are congruent. So you have to come up with a series of translations, reflections, or rotations that will make the blue one land on the red one. Now mine does not look congruent. Would you agree? Why does mine not look congruent but yours does? They changed the width of the scale on the y-axis compared to the width of the scale on the x-axis. 1 unit on the x-axis is smaller than 1 unit on the y-axis, and what that does is it distorts your graph. I liked this example, though, because that reminds me to tell you, do not change the scale on your graph. Go by ones, keep it the same for your x's and your y's so that it doesn't distort your pictures, okay? So you're going to look at your graph paper, not my graph paper, and you're going to try to decide, how would I make the blue land on the red? So what do you think, what transformation for sure do you see we're definitely going to have to do? Okay, a rotation. In what direction do you think? Okay, counterclockwise how far? Okay, so we're thinking a rotation counterclockwise 90 degrees. So let's write that down, that we think we want a rotation counterclockwise 90 degrees about the origin. Include your center. Okay, so if it's a rotation 90 degrees counterclockwise about the origin, then that means that we should be able to take the coordinates, switch them, and change the sign on the left, and that's where they should have landed. So let's check it. Let's take the A, and let's see if A prime really does match up when we switch and change the sign on the left. So what would A prime be if I take 1, 2, and switch it and change the sign on the left? Okay, -2, 1. Do I have a -2, +1 anywhere in my PQR? No, I do not, right? Okay, B, what would B prime become? -1, -2, and everybody with Weston that we're just switching and changing the sign on the left. Okay, C prime? -2, 4. Okay, so, but it does look like we need to rotate it to get it to face the same direction, agreed? So what we're going to have to do is graph this new shape in between and then decide what transformation do we need to do next to finally get the shape onto the red one. So sometimes it's more than one transformation, and you have to list all the transformations that will make them land on top of each other. So the best way I found is if I think it looks like a rotation, I do it first. I do a rotation, I find my new coordinates. If they aren't the same, then I graph those new coordinates. So I'm going to graph the point -2, +1. That's A prime. And then -1, +2, B prime. And then -2, +4, which is going to go off my graph just a little bit. That's C prime. So you plot yours on your graph paper. Now, I have had some students who don't see the rotation first. They see the other transformation first. I can't do it. I have tried. I've been teaching 20 years and I can't see it the other way. My brain just will not see it out of that order. When I look at this problem, I have to do my rotation first and then I can see what other transformation I need to do. If you can see it in a different order, that's totally fine. But for me, I have to rotate it so they're facing the same direction, graph that shape, and then now I can look at the green and the red and say, okay, how do I get green to land on red? What would we do? Translation. Okay, so once we rotate, we're going to translate. So translation, and then let's go directions. Left 1, down 3. Do you guys agree? So we're going to do a translation left 1, down 3. Safer probably to do the left and then the down versus down then left so you can make sure and write your rules correctly. So this is identifying and describing them. If I go left 1, down 3, every point's going to match up, right? All right, so now we want to write the rule. When you write a rule and there's multiple transformations, you're going to keep the arrow going. So X, Y arrow. The first thing we did was a rotation counterclockwise 90 degrees, which means we switched and changed the sign on the left. So that became negative Y, positive X. We did not go back to the original blue shape and then translate it, right? We went from this new shape in the middle and translated it. So we just keep the arrow going. We're going to take these new points and we're going to shift them left 1, down 3. So what would the rule look like? X minus 1. So remember, you're starting with X, but you're taking away 1, comma, Y minus 3. If it's a translation, you're adding or subtracting to the X and the Y. If it is a dilation, you're multiplying by the X and the Y. And if it is a reflection, you're just changing the sign of one of them. If it's a rotation, you're switching and changing signs. Okay? So this would be, all of this would be our answer for our proof, but it's not a 2-column proof. It's just a list of transformations that allow it to land on top of itself. Any questions? All right, I'm going to give you, we only have one left, right? I'm going to give you a few minutes for you and your partner to go ahead and try the last one on your own. Again, this is not a decide if they're congruent, it's a prove they're congruent. So they are congruent. You've got to decide how to make them land on top of each other. If we have some ideas kind of where to start. So those of you who think you have an answer, actually keep working. I'm going to graph this up here real quick first so you can see the graph with me when we talk about it. Obviously, you're going to need lots of graph paper for your homework, so make sure that you do have graph paper. So that was, let's go. Okay, so if you think you know how to get PQR, or excuse me, ABC to land on top of PQR, what do you think you would need to do? Or it can go the other direction. Maybe you did PQR and made it land on ABC. Suggestions. What transformations could we do? Okay, a rotation. What if you think it's a rotation? Which shape are you rotating? Okay, 180 degrees from PQR. So that would mean I would take these coordinates and I would switch them using my rule. When you switch twice, it takes you right back to where you started x, y. So the only thing that happens is you really just change both x and y's signs, correct? So this would become P prime would be at -1, 0 because you don't have a -0. Q prime would be at -3, +3. R prime would be at -3, +0. So if I graph -1, 0, -3, +3, -3, +3, and then -3, 0.
Pardon the interruption. Just a quick announcement before the bell rings. There is a very important IPS meeting during Encore today around 2:50. So if you are involved in that, please attend that meeting. Josie Martin, Jeremy So, Keegan Pugh, Warren Dozier, Jaya Schofield, Benjamin Bryant,
Remember, this is not due till
Cynthia
Friday,
Flores,
so you can keep
Melania
it,
French,
and that'll be turned into me on Friday. Carlos, the to get help from another teacher, a parent,
Rebecca
online. You have to show your own work. You are allowed to work with a partner in the class. So if you have another student in our geometry class that you want to work with, you guys can both work together, but you have to show your work separately and turn them in separately. But you're not allowed to get help from any other resources. You can use your book, you can use your notes, but nothing else. Right? Okay, guys, back up here. Did that work? Can we rotate it 180 degrees? No, and I don't see another transformation that would make red land on green easily. Do you?
If you reflect it and then do the translation.
Okay, so are you with me, Weston, that rotation, that didn't quite work? Okay, so I'm going to say that we're not going to do what's in red. Let's go to a different option. Anna, what did you say, reflection with what shape? How are we reflecting?
Well, I was talking about the red one. If you reflect that over the x-axis and then translate it.
If I reflect it over the x-axis, it's just going to look like this. If I reflect it across the y-axis, then it's going to land back over here.
And then you translate.
Okay, so that would be 3 transformations. I think we could do this a little quicker with just 2 transformations, although that wouldn't be wrong if you did all 3 of those transformations to make it work. Bree? If I rotate it 90 degrees, it's not going to land on the green one either. Did you actually do that and see where it landed? Mm-hmm. Right, so if I do P prime, Q prime, R prime, and I do a 90-degree rotation, did you say clockwise or counterclockwise? Counterclockwise, and that means I'm switching and changing the sign on the left. So this is going to become 0, 1, changing the sign on the left doesn't change it. Switching these, -3, +3, change the sign on the left. Switching these, I get 0, 3, changing the sign on the left doesn't change it. So 0, 1 is going to put it here. 3, 3 is going to put it here. And then 0, 3 puts it here. Again, you get to choose that, but Bree specifically said starting with PQR. So she was taking this shape and making it land on this shape. Okay? Are you with me there, Bree? Okay. So I don't think a rotation is the quickest way to work this problem. Did anybody come up with a different one? Ivan? Reflection. Reflection across what? The y-axis. Okay, which shape did you reflect? ABC or PQR? Okay, so if I take ABC across the y-axis. So let's go ABC across the y. That is 2 units away, so I would go 2 units across. 2 units away, 2 units across. This one is 3 units away, so I go 3 units across. Is that correct? And this is what my shape looks like. And then what did you do? Okay, so I'm going to go back to, you could do a rotation. Obviously, Weston helped us, but it would be multiple transformations. You can't just do a rotation and one other thing. You're going to have to do a rotation, then a reflection, then a translation. What would have been easier here, and so I'm just going to re-sketch these over here so you can see them. What would have been easier would be to reflect this shape, P, R, Q, across the x-axis. If you went across the x-axis, your shape would now look like this. So if I go across the X, it would now look like this. Is everybody with me? And then it's just a translation, and we could translate it left, 5, and down, I believe it's 3 is where it would land. So if you can find a different way to do it, that's fine, but make sure you're checking it. Make sure you're graphing in the middle shapes to see, is it really going to work? You can't just say, I think this is a rotation, and then write the rule without checking to see, did it land where it was supposed to land? So the answer here could have been, it didn't have to be, a reflection across the x-axis.
At the time. Thank you.
I would write this down so you have it to look back at, followed by a translation. Left 5, down, believe it was 3, if I did that correctly. Is it 2? Thank you. Down 2. And then your rule would be X, Y, arrow. If you're going across the x-axis, it's the Y that changes sign. Arrow, and then you would have X minus 5, Y minus 2. That's a minus sign there. Okay, but again, as Weston said, we could have rotated that, then reflected it, and then translated it, and that would have worked. We would have just had to have 3, and your arrows would keep going. Okay, so my best advice on the homework, persevere. Try it. If it doesn't work, try a different transformation. Don't keep trying rotations over and over again if they're not working. Try something different.